If you watched the two-part video about the exploitation challenge from the RHME3 qualifier, then you know I had some wrong assumptions about the heap. This is what I said in the video. We just have to find a sequence of operations where we get control of this pointer. In general, this should happen when we create some players, select one, remove some and add some again. As you can see, I imagined this is like the old school DL-malloc heap, with these basic chunks. When you free them, they are usually combined again to bigger free chunks, and thus you can allocate a new much bigger one in its place and write anything in that place. But this is not what is happening. I know Fastbins exist, but how the heap algorithm really works was not clear to me, and I never really spent time reading about it. So what are Fastbins? Free chunks are stored in various lists based on size and history so that the library can quickly find suitable chunks to satisfy allocation requests. This is already very different from the old school heap, as now the size of the allocated area decides what kind of strategy is used to manage the heap. You can imagine that there are different optimized algorithms depending on how you use the heap. The lists called bins, and there are, for example, Fastbins. These are small chunks stored in size-specific bins. Chunks added to a fast bin are not combined with adjacent chunks. The logic is minimal to keep access fast, hence the name. Chunks in the fast bins may be moved to other bins as needed. Fast bin chunks are stored in a single linked list. Aha! Another page says about fast bins. There are 10 fast bins. Each of these bins maintain a single linked list. Addition and deletion happen from the front of this list, last in, first out. Each bin has chunks of the same size. The 10 bins have chunks of size 16, 24, 32, 40, 48, 56. Size mentioned here include metadata as well. To store chunks for fewer bytes will be available on a platform where pointers are 4 bytes. Only the pref size and size field of the chunk will hold metadata for allocate chunks. Pref size of the next continuous chunks will hold user data. No two contiguous free chunks coalesce together. So what this means is that the player structure, which contains the stats and the name pointer, is so small that it will be organized by such a bin. And the use after free issue here is that we have a pointer into such a freed bin. That's why our strategy is actually to make sure that we allocate data that goes into the same bin as the player struct was before. Basically, we want to make sure that our name we enter ends up in the place of the player struct. So the name has to have the same size, or the size that is placed in the same bin like the player struct. So what is actually happening with the exploit is this. We add two players with 32-byte names. Now the player structs are placed in the same bins with their size of 24 bytes, but the names are larger and go in another bin. Now we select the second player, so we have the reference to this bin. Then we free the two players. And now we allocate a new player with a name of length 19, which means I chose a name that goes into the same bin as a player struct. So the first malloc allocates a player struct and it's placed where the first player struct used to be, and the name, because it is put in the same bin, is now get placed here, which used to be the player struct of the second player. Thus we can control the name pointer now. I think that makes so much sense. I'm glad I understood it now. I wanted to mention one more thing. After the qualification round was over, I went on IRC and talked to the other players, and that's when some really awesome people explained to me what was going on. After that, I felt kinda embarrassed on how wrong I was in the original video that I have already edited, but ultimately decided not to change it and instead make this additional video. Because yes, I didn't understand what was going on with the fast bins and my mental picture of the heap was wrong, I still ended up solving it. And I want to share my CTF experience with you, and my experience include having these wrong assumptions but still solving it. And I think this is now a good example of what is always happening in IT security research, because not everything is known and you don't have to know everything before doing stuff. The more experience you have, the better you are with educated guesses. And based on my experience with the old school DL-malloc heap, but knowing that the modern heap implementations are a bit more complex, I had a rough plan and it worked out, but in the end it wasn't exactly what was going on. But now I learned, and for the next heap challenge I will have a much better idea.